Okay, I'm making this video in my AP Calculus class, a review for their Unit 5 test coming up tomorrow. Okay, this is the multiple choice portion. You can watch the other video for the FRQ portion. So question number 1 starts off with this graph showing the distances from a reference point of a particle as a function of time. So which of the following points marks the closest, is closest to the point where the acceleration first becomes negative? So this is going to happen at point C. Whoops, I need to get this thing right here. Point C. Acceleration first becomes negative. That is where our graph changes from concave up, right, where we have a second derivative that's positive. Sorry, that's supposed to be S of t, not F. Okay, so second derivative is positive there. And then here, after B, the second derivative is negative because our graph is concave down. So this is where our graph is changing from concave up to concave down. Okay, that's the first part. Where it first becomes negative is at point C. Okay, number 2. The graph of f double prime is shown to the right. Which of the following is true? So let's do some investigation here. The graph has a point of inflection at x equals -1. Okay. What is the y value at x equals -1? 0. Yes, so the second derivative here at -1 is equal to 0. Okay, is that how we get a point of inflection? Yes, it is. So that one is true. Okay, where the second derivative is 0 is where we have a point of inflection. Okay, so it's negative on the left and positive on the right. The original graph would go from concave up to concave down. Okay, number 2, the graph is concave down on the interval from -1 to 3. Okay, so what do we know about the positivity of our second derivative here? Well, we know that it's below the x-axis, which means it's negative. So if we have a negative second derivative, that means your graph is, in fact, concave down. Okay, and everywhere the graph is positive, the graph is concave up. Okay, well, what about part 3? The graph is increasing at x equals +1. So we have -3 as the y value. So I would say this is no, because we have a negative second derivative. Okay, so your graph should be decreasing there. So number 3 is not correct. It is decreasing at x equals +1. So it looks like the correct answer is D, 1 and 2 only. Okay, so we have some graphs that we're analyzing, and we're putting together f prime, and f double prime. Okay, the graph, the first derivative, and the second derivative. Okay, number 3, a portion of this function is shown at the right, continuous. So it's a continuous function. There are no gaps or holes or asymptotes. Which of the following is true? Does the mean value theorem apply on the whole entire interval from -2 to 2? Okay, so continuous, check, but is it differentiable on that interval? No, it's not. There is a cusp right here. Okay, anytime there is a cusp, you have a not differentiable function. So I is wrong. It is not applicable. Okay, what about the extreme value theorem? Does that need to have differentiability? No, just continuity. And it tells you it's continuous, so number 2 is correct. And what about number 3? That there is a value C where the y value is 1.2. Is that true? Yes. Okay, and that is the which theorem? The intermediate value theorem. So number 2 and number 3 are correct. Right, somewhere in here there is a y value of 1.2 because it has a lower value of, a half, and an upper value of +2.
Can you explain explain 2 again?
Okay, number 4. Here we have a nice quadratic. What's the maximum value on the interval from -6 to -1? Okay, so we have to try our endpoints, and we also have to figure out where this has a well, we're going to see if it has a maximum. Okay, so let's take the derivative, h prime, and see where that is 0. So we bring the 2 to the front and make it a -2x minus 4. Okay, we want to know when is this 0. So 4 equals -2x, so that happens at -2. Okay, so there's 3 points that we have to try. We have to try our endpoints, and then we have to try -2. Yes, so 1/2 times 2 is, -1. So -x, so x equals -4. Mi siento, gracias to my students for catching that. -4 is the other point. So we're going to have a, well, let's see, what is that -4? Is that a max or a min? So to the left of -4, if you plug in -5, we get a positive on the left, and you get a negative on the right. So yes, sure enough, this is going to be probably the maximum value. So when we plug -6 and -4 and -1 into your function, we'll figure out what those y values are. So when I plug in my endpoints of -6, I get 10 as my y value. When I plug in -4, I get 12 as my y value. And when I plug in -1, I get 7.5 as my y value. So the maximum value, the y, is 12 when my x is -4. Okay, so the answer is 12, not -4. Okay, number 5, so the back of our paper. We want to find the derivative at x equals 1. So this is the slope of the line when x equals 1. So here we have a fraction, aka quotient. So we're going to have to take the derivative using the quotient rule. Okay, low-D high minus high-D low over low-low. Okay, there is your quotient rule. Now if you want to, we can plug in +1 right now without having to simplify at all, since this is a multiple choice question. So when we're plugging in 1, let's see what we get. We get 1 minus 2.
Plug in 1 before we do it?
1 minus 2 is -1 times 4 is -4. Minus here, minus 4 minus 3, because 4 times 1 is 4. 4 minus 3 is 1. 1 times -2 is -2. So this becomes a 4 plus 2 in our numerator. And on the bottom, 1 minus 2, so that's -1 squared is 1. So it looks like when we do all this fabulous stuff, -4 plus 2 is -2. All right, let's look at number 6. Here is the graph of f prime. Which of the following statements is true about f? Okay, so it says f is decreasing from -1 to 1. So if f is decreasing, that means that f prime has to be less than 0. Okay, and truly f prime is not less than 0 between -1 and 0. Right, it's above the x-axis, so A is not going to be correct. F is not decreasing on that whole entire interval. Okay, x is increasing from -2 to 0. Well, that might be true because your derivative is above the x-axis. So this one might be true. Let's see if there's another one that would overrule it. F is increasing from 1 to 2. No, that's not true because your derivative is less than 0. So it's not increasing. And f has a local minimum when x equals 0. Okay, so let's see. That means it's going from a positive to a negative. Nope, a positive to a negative means it has a local max. So part D is lying also, which means B is the only thing that is correct. F is increasing from -2 to 0 because your derivative function is above the x-axis, aka positive. And when your derivative is positive, your f is increasing. Okay, number 7, 8, 7, and 8. Right? You need to recognize this for what it is. This is talking about the derivative of this function. Okay, this is the quotient, difference quotient. Okay, this is the way that we learn how to do a derivative at the first or second week of school. So you need to recognize this as just trying to find the derivative of the tangent of 3x. Okay, that is what this is asking you to do. Find the derivative of the tangent of 3x. So according to my chart, if I just had the tangent, the derivative is secant squared of x times x prime. Okay, as in the derivative of whatever I'm taking the secant of. So in this case, I have 3x, which means I'm going to have the secant squared of 3x times what's the derivative of 3x? 3. So B is going to be the correct answer. 3 secant squareds of 3x. Remember, it's just the derivative of this function.
I just don't see how we know that it's just that.
Okay, number 8. We're just trying to take the derivative of natural log of 2. Okay, which sounds like a strange thing to do. I agree. But let's see, what if it were just an x? What's the derivative for natural log x? That's just 1 over x times x prime. Okay, so in this case, what is our x value? 2. So the natural log of 2 is 1/2. Just done. 1/2. 1/2. Okay? Natural log of 2, derivative of natural log of 2 is 1/2. Because the natural log is 1 over x. Okay, number 9.
Wait, hold on, I'm tripping.
Number 9. What happens when we plug in 0 to the top and bottom? We get 0 over 0. Okay, that is the indeterminate form. So we can apply L'Hopital's rule. We can apply L'Hopital's rule and take the derivative of the top and the bottom. Okay, so we're going to take the limits as x approaches 0. What is the derivative of we'll just do the bottom first, right? What's the derivative of x?
1.
That's just 1. Now what's the derivative of the top? 1 over 2 root of x plus 9. Right? The minus 3 cancels out. It's no longer there because that's a constant. It is not involved in the derivative. Okay, so in essence, we're taking the limits as x approaches 0 of 1 over 2 roots of x plus 9. Okay, so I've just simplified. No longer am I dividing it by 1 like I was right here. It's the same thing as that, just the fraction. Okay, so now let's try plugging in 0 again, and what do we get? 1 over 2 times the square root of 9. And the square root of 9 is 3. 2 times 3 is 6. So 1 over 6. So this is a L'Hopital's rule, because when we plug in 0, we get 0 over 0, which is the indeterminate form, which means you can apply L'Hopital and take the derivative of the top and the bottom until you no longer get an indeterminate form.
Okay, wait, so the derivative of the bottom is
Number 10, let's try once again some direct substitution. So let's plug in 1/2 into both of our values. That's 1 plus the natural log of 2 times 1/2 over 2 times 1/2 minus 1, which is 1 plus the natural log of 1, I believe, over 2 times 1/2 is 1. 1 minus 1 is 0. So if I have 0 on the bottom, this is a undefined function, and the limit does not exist. So the limit of 1/2 of this function does not exist. You would have a vertical asymptote there, because that's how we get a 0.
So are you able to just plug in 1/2 and then just simplify it out?
Plug in 1/2, right? That's exactly what we do on number 9. We plug in 1/2 and we get 0 over 0, which means we have something else to do. We plugged in, well, 8 and 7 were just knowing.
So on 10, okay.
Okay, number 11. A box is to be built from a rectangular piece of cardboard that is 40 by 25. So this is our optimization problem where we have to cut out corners from our box in order to make it into a rectangle. Okay, so this is a volume where we have a height of x. Okay, the length here is going to be 25 minus 2 x's because you're cutting off a corner from each side. And the length is going to be 40 minus 2x because we're cutting off the same square from each end of our piece of cardboard. Okay, now once again, there are lots of ways that you could solve this out. Okay, you can distribute one time and then do the product rule, or we can multiply it all the way out and then do it then. So whichever way you want to do it is good with me. So this is our volume formula, which now we have to take the derivative of in order to figure out what the maximum value is going to be. So I am taking the derivative of each of these terms. So 4x cubed, the derivative is 4 times 3, 12, x squared. You multiply 130 times 2 and get 260x plus 1,000. Okay, now this is something that's probably can be simplified a little bit by dividing everything by the same number, probably not 12, but 4 would work. 3x squared minus 65x plus 250. Okay, and believe it or not, this is a factorable quadratic. 3x and x. So this comes out to be your factorization of your quadratic. We want to know when it equals 0, right? Because that's going to be our maximum. We want to know when the slope is 0. So it turns out that it happens at 50 over 3 or at x equals 5. Now 50 over 3 is a number that's longer than any one of these sides of our box to begin with. So this one is not a feasible answer. So x equals 5 is going to be the length that we're going to cut off from each of your corners, or rather, yes, corners, in order to fold up and make a box with the largest volume. Okay, yes, that's a lot, but I believe that because of your amazing brain, you can do it. Good luck.